Right, let's start. So I just started the screencast. First, are there any questions? Any questions? Okay. Next, let's go around and do some quick status updates about your projects. I've collected all the homework this morning, so maybe you could say something about what you actually ended up doing. So I'll start right here. Just say like something really quick about what you did so far.
I set the bar pretty high with this one. I was originally planning on. Oh wait, what?
And make sure you say what your project is on, because I doubt anybody will remember from before. What your project's on, what you've done. Quick, go.
So in set the bar. So I was originally going to write like a PHP website that would be like a Polygons implementation essentially, but do battle simulation as well. And after fumbling around with PHP and not being able to find a server, I decided to just write it in Java and utilize 142's drawing panel class, if anyone's familiar with that, to plot graphical information about it. So it's still doing the same functionality, but not nearly as impressive looking. But yeah.
As a plan, you'll have a program that people will download and then run on their computer?
It'll essentially just be like a directory, and they'll have to run it through their like whatever text editor they use, JGraphs or
like an IDE. Okay.
Exactly.
Got it. Okay, next.
My group is working on a Python program to decompose instrument sound files and figure out why they say different things sound different using Fourier transforms.
And
we finished all the code, all the back end, and we've created a website for it just to show off what we've done. And so right now we're just working on kind of making a GUI so it's more trustful and maybe adding some other interesting features to it.
nice.
We're on the same page.
Okay, cool. All four of you?
Three.
Okay, next.
I'm not in a group.
So what do you do? So what's your project on?
I'm not in the class.
Oh, if you were going to do a project, what would it be on? What are you interested in related?
I really don't know. I think maybe it'd be cool to do some sort of analysis of graphs, maybe
Like
find
vertices and edges graphs?
Yeah,
Yep.
like find out if a graph is planar or something like that. But that seems really hard.
There's an isPlanar function in Sage. And if you pass in an option, it'll even, if it says it is planar, it'll draw a planar embedding of the graph. And you can also compute the genus of a graph as well.
What's the genus?
It's the smallest genus of a surface that you can embed the graph on the surface with no, of that genus without any crossings. So like genus 0 is almost the same as planar. In case you're curious.
That's cool.
It's a lot of complicated code. Yes, what are you?
I work with my partner and he's not here.
Oh, okay. So what are you guys doing?
We fundamentally develop a Java code and
Does what?
a Java code like to run our. We have several data files,
Uh-huh.
so we use them as an input,
Mhm.
and then we predict the stock price as an output.
Got it.
And for the future, we plan to add some function about how to graph those data out and to see it something like that.
Nice. Cool. All right. Start here. What's up? What?
Is there like a computer program, like a Sage package,
Mhm.
GNU, which outputs the Go game, but its output is like really non-graphical and not like reading. So I was trying to change graphics, like better output.
Cool. So you're making a Sage package for GNU Go that is not totally ugly. Yeah. Or it has graphics. Okay, cool.
I'm writing a program to calculate the covariance of like a big list of stock returns, but by dividing the list and doing it in parallel.
So parallel computation of covariances of stock returns. And how's it going?
I'm like almost done with it. I just have to add the parallel decorator.
Nice. Cool.
I'm kind of finished my code, like most of my code, but I'm just trying to figure out, because I'm using your code, so there's some glitches happening, so I'm trying to fully understand.
Was this the project on rotating polygons?
Yeah.
Okay. So you've mostly written code and now you're dealing with bugs.
Yeah.
Got it. For rotating polygons. Okay.
I'm working on exposing an API in Python of kind of like Sage MATLAB and creating ideas with Sage.
Cool. So an API for Sage Math Cloud / Sage.
I'm working on the 10 million in the state version, and right now
Actually, I finished the code, but the outcome is not what I expected, so I still need to make some correction.
Okay, so you have a buggy implementation of the Sage worksheet of the Hangman game. Cool.
My project is a sample model. I just finished it, but I don't know code. It's doing a little slowly. I don't know why.
It's the what model?
Sample model.
Sampow?
Yeah.
What does that mean? I'm totally ignorant. What is that?
I think the Sage is the Sage has also
Uh-huh.
it's sample SANDPRLE. That's right.
Sand pile?
Sand-
Yeah,
sand pile.
Sorry,
Oh.
I pronounced
No, that's okay.
Sand.
Okay, cool. So what's it for?
when I find I use a pattern writing it, I finish it, but I found it the whole. I mean, the run is really slowly. I don't know why.
Okay, but what is sand pile? What does it do?
I just want to create a picture.
For drawing pictures? Or wait, I don't understand. What is the sand pile model for? Like, what's the application? Or like, why are you interested in this? I know that many people are. I'm just
Yeah, I know this model because some of my friends also learn mathematics. Told me it's a really interesting model.
cool.
Yeah, learn something about this and use the pattern to write it because it's I think it's really funny because you can create the picture. The picture is sorry.
That's okay.
And maybe I can try.
Cool. So basically, at the end of the day, you've written some code for computing with something called the sand pile model,
Yeah,
and it's slower than expected.
really
Cool.
slowly. I don't know why.
We'll figure it out. Okay, next.
I'm using the Interact decorator to create a program that mimics the functionality of the Wolfram course assistance. But in addition to that, each function has a little checkbox that will show you how to do that process directly in Sage.
Nice.
So it's kind of like a tutorial on top of the course assistant.
Cool. So you're doing something related to Wolfram Course Assistant in a Sage worksheet with interacts. Got it.
So I'm working on the scheduling
Mhm.
on the back end. I'm still trying to figure out how I'm in the right capability of the user interface.
Got it. So course scheduling, back end done, front end not done. Got it.
I'm doing odd perfect numbers. I wrote some lame code to search for odd perfect numbers. Of course, it's not going to return any result. And then I have a 10-page so far LaTeX document talking about even perfect numbers and necessary conditions and stuff about
Oh,
those
cool.
sometimes. And then it'll probably be it's probably about halfway done because it turns out a lot of those theorems about odd perfect numbers are really difficult to understand.
Yeah. Cool. So odd and even perfect numbers, you've written something up and you've written some code to kind of first test that there aren't very many odd perfect numbers. Cool.
My project is about analysis of dynamical systems, and
Mhm.
it explains the stability of the fixed points and what kind of rotations of traction and the traction field of the
Nice.
system of the dynamical system. And I'm trying to get some kind of user interface where they can click on the direction field and it shows where the output is going. But I am having some struggles.
Yeah. Cool. Right. So basically, a dynamical systems explorer, I guess.
So I've changed my project around given learning about BioPython.
Mhm.
I'm going to work with running a class that would model reaction diffusion equations, which are partial differential equations. And getting into that, I found that there aren't really good numerical methods for solving those.
Mm.
So now I'm implementing the most basic finite difference. It's called the Crank-Nicholson algorithm for solving that. And I think I'm just going to implement several different
right? So implement some PDE solvers and then use them to try to solve
Model like some
Some-
pattern forming stuff.
cool, some biology-inspired PDEs. Great.
I'm doing fluid dynamics, modeling computer Stokes equations. I convert all my rendering code over to JavaScript because cython is taking multiple seconds for each thing. So I do front end done, but I'm having some trouble putting the linear equations into the system.
So you're writing entirely in JavaScript a Navier-Stokes simulator. Is that right?
Writing everything in cython, with the rendering.
Okay. So in Python, you have the Navier-Stokes backend compute stuff, and then all the rendering is done entirely in JavaScript for speed purposes. Awesome.
I'm just working with discrete probabilities and whatnot in there.
Mhm.
Right now, state you can define continuous ones, like there's preset ones in there, but there isn't for discrete.
Uh-huh.
And then if
Ah, I
this,
see.
you can make your own random discrete ones.
Mhm.
You can't make your own continuous, so I'm trying to.
Interesting. So there's a ton of different continuous probability distributions, but there aren't any discrete ones in Sage anywhere. So you want to make it so there's like, a bunch of standard ones. What's an example of one besides uniform that people care about? There you are. Okay. What else?
Well, going to song processes.
Okay, cool.
Those are like the two main.
Yeah.
And it's going to stem down from there.
Yeah. Are there also like operations combining some? I'm just imagining like a 20-sided dice and a 6-sided dice. Combine them and you get something.
I'm adding a lot of methods in there.
Mhm. Nice, cool. So basically discrete probability algebra kind of stuff. Great. Yeah.
So we're working together. And
Mhm.
we're doing like a class for differential geometry for a class we did.
Oh, nice. Uh-huh.
And so I'm plotting curves of one variable used to move surfaces of two variables.
Mhm.
And both of us like have different parts for one for current equations. And I think we both got those done.
Mhm.
And then so now we're working on plot functions. And I think we're both having problems with that.
Okay. So functionality for visualizing things in differential geometry. Got it. And you're having difficulty with the actual plotting part, but not with the previous step, whatever that is. Okay.
Like getting the equations,
Big-
trying to get the frames and stuff.
Okay. But actually making it appear on the screen.
Yeah.
Got it. Okay.
I'm working on a caching system right now. There is a caching system in place, but it uses a kind of a dictionary-like relationship with files.
Right.
And instead of doing that, I'm running it in a SQL database. So for functions like factorial, or sorry, like factor.
Yep.
Factor large numbers is a very costly process. And also that factoring, like factoring the number 10,012 is going to be the same now and later. So basically you can access that number twice and then just see that it's in the cache and not make that calculation. I'm on the fence about making just a decorator function for it, or actually returning a new class for each casting function.
Mhm.
But it's still exciting.
Cool. So making a database cached function decorator or functionality in general.
Yeah.
Cool.
The decorator function is a lot lighter, which is good
Mhm.
for Sage and Python in general.
Mhm.
It makes it more difficult to have the option to delete or recalculate.
Right. So maybe you can have the decorator built on top of something else that has more functionality. So you have the best of both worlds.
Yeah, then I'm just thinking about how to do it.
Right. Good point. Yeah. You could have like a method that gets added to the function or something.
Yeah, I like that.
Cool.
My project I'm working on traveling setup and problems between projects that reads real-time arrival times and walking distances in the eyes, so we don't really need to do the project we're trying to find. See how long it takes to walk. How to understand what we're doing. Potentially the project at the time, so we have to change that.
Cool. So figuring out the optimal way to have fun at a theme park. Right? Awesome.
I'm working
The what? Bus schedule. There's always a bus schedule project. That's cool. There always is. Yep. And
I come up with a metric from there, a matrix I'm doing 2 months, 2 tasks,
Mhm.
nights are, and it is basically and also it's based on the distribution populations, like the class,
and they give you that sort of data. Nice. Cool. All right. So the bus scheduling project, and you have data. How far along are you with this? You have the data.
So I'm just writing the program now. I've come up with a metric.
Cool. So you started writing code. Good. Right.
I'm doing a Sudoku project, and I was having a hell of a lot of issues with it at first, and I kind of started over from scratch, and I've created an interactive Sudoku like fill-in,
Mm-hmm.
and then you create it, and then you can check your entries that you do,
Mm-hmm.
and then if you have errors, it tells you where they are,
Mm-hmm.
and it checks that it does have a solution.
Cool.
That, like, checking that it actually has a solution takes a long time.
Huh.
Because of the built-in solve
Uh-huh.
Sudokus.
Uh-huh.
But I think that I might try to write maybe cython code
Uh-huh.
to permute the
Ah.
Sudoku matrix.
Surprised when you say a long time. I mean, I'm a little surprised because I thought the solve was usually very fast. Just a little surprised by that. But
Well, it kind of depends on like what matrix you
Yeah.
put in.
that's true.
So
Cool. All right. So wait. Summary is graphical Sudoku game.
Yeah.
Good. Okay. All right. And what has happened since last time you said that?
So I decided on the inputs I want to use for all functions that are available for the object, documented it all, and I started with a bare bones implementation, but made my way to figure out how I wanted to represent it.
Cool.
That's all solid. So it's just I need to do more stuff with like the hashing functions and
Mhm.
that, and
It just occurred to me that if you look at the source code of BUP, a very badly named but awesome program. It's on Git. So github.com/bup. And it's a Python program that, whoops, I misspelled that backs things up. So it's called BUP, back things up. And it has a Python it has an implementation of a Bloom filter, and it's in C, and it's linked from I've never actually looked at it, but it may be worth comparing to see what's there. So
right now I'm using the
BUP.
same set.
Yep.
I was gonna see once it's implemented if I like which I decide on
Yeah. So you may want to look at this though. It has definitely in here. It has like when you build it, I know that it. Let's see, I think it's in lib. Just for comparison, it's going to be one of these things, I guess. Bloom.py. I don't know. I think Bloom.py implements a Bloom filter and then maybe does something in C. I don't know. Maybe it's all in Python. Anyways, you might want to look at this for comparison. So. I guess it's in Python. Who knows? Maybe you'll look at this and then make it faster. That would be cool. Okay. All right, so implementing a Bloom filter in Python and possibly cython. Okay.
I decided just to go through the sets. I've got a first draft of code done, first draft in Python. It's a little too pixely for my taste.
Mm-hmm.
It's kind of a small image, so I'm
Mhm.
a better way of rendering it. It's a little bit bigger, short.
Cool. You might find today's example of plotting the Mandelbrot set with arbitrary size relevant. So I'm going to do that in a second. Okay, is that everybody? I think it is. Okay. So that's status reports, questions, homework. So I collected homework 6, I redistributed the grading, etc. If you're missing something that you should have now, let me know. So let me show you homework 7 right here. So I assigned this just today, and it has 3 problems. The first one should be pretty easy if you're paying attention to class, and it's simply to take the class that we created last time on Friday and add a couple of methods to it, namely mean, standard deviation, and I guess variance is already there, and also add a method that adds up the signs of all the numbers. And there's a little bit of a challenge there. I want you to do it in such a way that it's pretty fast, faster than the really naive sum of sine of x for x and b would be. So you'll use a trick which I'll show you in a second that allows you to do this. I'll show you with, instead of using sine, I'll use x for something, but I'll show you this in a minute. Okay, so that's the first problem. The second homework problem is to go to the Cython website. It has on its wiki a list of projects that use cython. So let me click on this link to show you. So here they are. And this is all that they list. So it just says others ... And what you'll do is choose 5 of these and say something about how they use cython. Okay? They could use cython, maybe to optimize one little function somewhere in their core. It could be the entire thing's written in cython. Just say something, and the question makes it more precise. To say something about specifically how cython is used in the project and to what extent it's used. This is a wiki page on GitHub, by the way. And since you all have GitHub accounts, if you want to, you can probably edit this page. I noticed, for example, I tried clicking on that link, and it's already broken. So I'm sure that with a little Googling, you can figure out where the LXML homepage is. Somebody should probably fix that link. Also, I'm pretty sure that this is not a comprehensive list of all programs that use cython. So by the way I phrase the question is you should choose 5 of the projects here that do something that might seem interesting or relevant to you at some point in your life, okay? So for example, the guy who left and is implementing finite element methods for solving differential equations might want to look at FemHub because it does that already in Cython. So if you're interested in, I don't know, OpenCL, whatever that is, then you might want to do this one. Or if you're into astronomy, you might want to look at Captine package, whatever that is. Or if you're in biology, molecular phylogenetics. If there's something that uses Cython that isn't listed here, which you could probably find things that you're interested in that use Cython, not listed here by typing Cython and then something after it into Google, you can add it to the wiki page, and then you could do your homework problem on that particular one. So I'm sure that this is far from comprehensive. Okay, so that's what that problem is about. And then the third problem is to make a little presentation meant to be about 5 minutes long about your project using LaTeX Beamer. This is partly to get you to think about how you might explain what your project is about with a couple of slides to other people. It's also just an exercise to learn something about LaTeX Beamer. LaTeX Beamer is simply a package for LaTeX, or a style of LaTeX. I'll show you, if you look at the homework, you'll find that, go to the directory where the homework is. In your project, you'll find there's a directory homework 7. In there, there's a subdirectory Beamer. And if you click there, there's a tex file at the bottom. And if you click on that, you'll see that you have this LaTeX document, and each of the slides is wrapped in begin frame, end frame. And so each of those gets turned into a slide. And otherwise, it's just standard LaTeX. Okay, so here's what it looks like. And you can just change the title, change the author, put some text in between the begin frame, end frames that describes your project. Do that a couple of times, you're done. So that's what that particular exercise involves. You're not at all required that when you do give the final presentation for your project that you use this, because this is partly just an exercise to learn about a different tool for creating presentations that's different than using, say, PowerPoint. Because probably many people here have created PowerPoint presentations. LaTeX Beamer makes things that kind of look like that, but they also allow you to nicely include mathematics or anything else that you can do in LaTeX. Okay? And LaTeX Beamer is extremely popular amongst math and physics people for doing presentations. If nothing else, when you go to a conference or watch a talk by a math or physics person, you'll be able to sit back and go, oh, they're using LaTeX Beamer, because you'll recognize the styles and so on. Also, if you Google for LaTeX Beamer, you'll find that, for example, there are tons of different themes. Warsaw was just one I filled in here, but there's like dozens of different color schemes and so on that you can modify. So just try making some changes. So that's the homework assignment. Okay, done with that. Any questions about the homework assignment? I decided, by the way, to just make it officially due on Monday at 6 a.m. So do it before Monday, but I don't need you to stay up all night until 6 a.m. to do these. But I'm going to actually collect it at that point in time. I've actually pretty much always done that so far anyways. There you are. Yes, the last day of class. So it won't interfere with finals or anything in other classes that you might have. There's no final exam in this class. The last thing you do is the last day of class, I get your final project, and then you're completely done with the class. Okay, yes? No. In fact, you may get a little feedback during your presentation and want to modify your project a little. Wait a minute. What I said is not exactly correct now that I think about it because of the peer grading of the final project. So you can't be completely done the moment you turn in your final project because you still have to peer grade the other people's final projects. So, and now that I think about it, didn't I actually, I may have to backpedal for a moment because it is on the syllabus exactly when things are due, and I think that I'm just wrong. How am I going to do that? Yeah. Okay, I take that back. I am completely wrong. In every course I've ever taught in the past, that's been the case. But due to the pure grading of final projects, it's impossible for me to make the final project due on the last day of class. Otherwise, you guys would have to sit there and grade projects during finals. And I'm pretty sure that it's a bad idea to give you a bunch of work to do during final exams. You should be focusing on final exams for other classes. Unless you disagree with that, but right? You want to focus on your finals. So this is pure grading of, and then the thing that's in the of is as indicated, okay? Which should be clear from this. So no, the final project is due on May 30th, and then you will get everybody else's final, you'll get a couple of final projects that you'll grade, and part of your grading will be influenced by the presentations that people make about their final projects. Okay? In other words, your final project is due pretty soon because it's now May 12th. So I will stick to this schedule as indicated. On the other hand, the statement I made about you being done with the class at the end of class, the last day of class, is still true. Okay, any questions? All right, just to reiterate, I'm not changing anything at all from what I said on the first day of class, despite having incorrectly stated something for a moment just 2 or 3 minutes ago.
So is the final project actually going to be due on Monday?
That is a good question. That would make okay, so that change would be completely reasonable because people do tend to work on things like this a lot over the weekend, and you can still do the pure grading easily enough. So is anybody opposed to me moving this Friday, May 30th deadline to Monday, whatever it is, I guess June 2nd? Everybody in favor of that? Yes. Okay, I will make that change, which is pretty harmless regarding the class right now. Not there. What do I edit? The README. So I'm going to literally make it now. Maybe. Edit. Okay, so where was that? Assignment schedule right here. Something wrong with. So I'll make it Monday, June 2nd at 6 a.m. Everything's due. It's not a Monday. No, I wrote June 9th. Okay. Monday, June 2nd at 6 a.m. We're basically done, except for grading other people's stuff. Okay, official change to deadline for final project. Done. Okay. Good question. All right, so now let's move on. The rest of the 20 minutes we have, I'm going to talk about cython, and it's going to be basically some slightly more advanced functionality. And then that will mostly conclude what I'm going to show you involving cython. So what the takeaways should be in the next few minutes are that you'll learn how to, make this a little bigger, to create a standalone cython module that is code that's completely, you'll make a separate file that contains some cython code and that you can build and then import into a Python or Sage process or worksheet or whatever. So I'll show you an example of what's involved in doing that. And then I wanted to show you cython support for NumPy, but when I tried using it, it was all completely broken. So I'm not going to show you that. Or maybe I'll show you something quickly, but I won't be able to demo it, unfortunately. I'll show you a little bit of this stuff, but not so much. The main thing I want to show you is standalone cython module. So there's an example of computing the Mandelbrot set, which is in the cython documentation on the cython website. So let me show you that. That's what it looks like. So if you go to cython.org, this is the website for cython, which is basically, I guess, a sales pitch with some links. And then if you go to documentation, there's the cython documentation and the cython wiki. And let's see, cython wiki is where we'll look first. It has a bunch of links, and one thing is example. And that's an example of the Mandelbrot set. So here's where it's at. I'm just kind of giving this, I'm going to show you a modified version of this example. Okay, so that's where this comes from. So now what I'm going to do is show you a file which is not inside a worksheet or anything, though of course you could put it in a worksheet. And then walk you through it line by line. Whoops, let me just click on File here. It's called mandel.pyx. So the extension for a cython code file is .pyx, just like with Python it's .py. The X is supposed to indicate that Cython gives you extensions to Python. In the world of Python, there's this idea of writing extension modules to Python that came long before Cython and so on, which involved writing C code, which would get compiled to a shared object library, and you could then import it into a running Python session to get C-level speed in Python. And much of Python is implemented as these extensions. And secretly, really what Cython is it's a language that looks like Python, lets you write C extensions, and it automates the generation of the C code. Okay, so here it is. It's inspired by this post. So at the top I have some imports, just like in normal Python. And then I have a function, mandel. So the Mandelbrot set, if you don't know, it's a subset of the complex numbers where if you iterate the map z squared, or sorry, z goes to z squared plus c, it's not bounded. So because you're math people, you probably know this already, but just write, z goes to z squared plus c. So if you take a complex number c and you start with 0 and you just keep iterating this over and over again, the first value you get out is c, then you get out some other random value. You just keep doing this over and over again. For a given value of c, for example, c equal to 0, either 0 will go off to infinity or it won't. So like if c is 0, then if you keep squaring and you start with 0, you always have 0. So 0 is in the Mandelbrot set. Whereas some other values, when you iterate, you go off to infinity. So in a computer, you can draw an approximate picture of this by, instead of iterating forever, you iterate, say, 50 times, and you see whether or not, instead of going off to infinity, you see whether or not it's big for some definition of big. And you get a neat-looking picture as a result. Okay, so that's the Mandelbrot set. And this function right here is a cython function that takes as input the real and imaginary parts of a complex number, and then very efficiently decides whether the resulting point is in the Mandelbrot set, where that whole thing is in quotes. Really all it does is iterate this function 20 times by default, and checks to see whether the result is bigger than or equal to 2 in absolute value. So it says 4 there because we're not taking the square root. And what this is just a little bit of code that lets us square a complex number and add c to it without having to actually work with complex numbers. It's just a little bit, it's just like an ugly formula that does the same thing. Okay? So that's what this is. And not only does it tell us yes or no, whether it's in the Mandelbrot set, it tells us how many iterations are necessary until your number suddenly got big, which allows us to color the point in some nice way, depending on how quickly it's getting big. Okay? How quickly 0 is getting iterated away from the origin. Any questions about this? Okay. And then there's one thing I haven't mentioned before. When you define a function, if you put c-dep before it, it just gets turned into a straight c-level function. If you put inline, then it tells the compiler it can inline the function. So instead of doing a function call, it actually just puts the code right in the place where you're calling the function. So it's a little optimization. Okay, and now there's another function, create fractal, which takes as input various parameters, basically describing what the box is where you want to look at your fractal. And then image is a 3-dimensional NumPy array. NumPy, this library, it's an amazing library. It's kind of like MATLAB, or it provides similar functionality to MATLAB, but instead of focusing on 2-dimensional arrays, it allows you to work with n-dimensional arrays. So you have in this case 3 different indices, I, J, and another index in the other direction, which keeps track of the amount of red, green, and blue color. So I'll show you where the array is created at the bottom. So right here, this makes a 0 array, and it has 3 different directions, size, and 3. So it's like if size were 500, it would be a 500 by 500 by 3 array. So you can think of that as 3 500 by 500 arrays stacked on top of each other. NumPy is incredibly good at efficiently working with n-dimensional arrays, like 5-dimensional arrays, whatever. So it's really good for certain types of data modeling that might come up in, I don't know, fluid, like Navier-Stokes type stuff. I don't know if you're using n-dimensional NumPy arrays in your project, but probably want to, etc. And then it does things like plus 125, that adds 125 to every entry of the array efficiently. Like very simple notation. Okay, so that's what these are. And so the code just goes through every XY position in our fractal and determines whether or not the point is in the Mandelbrot set, and moreover, actually how many iterations were needed to see that it was flying out of the, that this map right here was kind of, that when you iterate 0 repeatedly, you're going away from the origin. So it then chooses a color based on that, and then fills in the 3rd dimension of the array using that color. Okay? And it's cython code, so in various places, data types are defined. And this is all in a standalone file, mandel.pyx, a separate file. Okay? And now, so that was the function mandel. Here's the function create fractal, which just runs through and does this. And then finally, here's a demo. And this is a part that might be interesting to you if you want to draw a high-resolution image. Here's how it works. So you make this array of all zeros, and then you add 125 to it. You should view the entries in this array as defining RGB colors between 0 and 255. 125 is just like right in the middle. It's kind of a neutral color. And then it runs the code to modify this byte array. So after you run the code, the entries in the byte array are all kinds of interesting colors. And then at the very bottom, there's some code. This little block of code here takes that array and turns it into a PNG image directly. Yes?
So I'm confused by your
Yes. Mhm. Yes. Yeah. NumPy has this idea of broadcasting, which is what they call it, where you can do things like add a scalar to an array, and it has semantics. You can even add arrays with different sizes, or like you can do all kinds of operations with arrays of different sizes. It has rules for how it will result in another array. It's extremely disturbing to me as a mathematician. For example, if you made a square zero matrix, like without the square dimension, and then you add a number to it, it adds it to all the entries rather than to the diagonal entries, which is what you do in linear algebra. And if you make two-dimensional arrays with NumPy and you use the asterisks to multiply them, it's component-wise multiplication, not matrix multiplication. So there's a lot of things that are very good from the point of view of just manipulating data with NumPy arrays that the data manipulating people love to use, that make the mathematician, kind of the algebraic mathematician in you, uncomfortable, as you may have been for a moment. But that's just the way it is. If you look at matrix multiplication operator in Sage Develop about a month or two ago, there's a huge discussion about this sort of thing, since some Python developer wanted to add a new matrix multiplication operator, which is two @ to the Python language. And there's a lot of feedback about why would we even want to do that? We just use asterisks for matrix multiplication. But the NumPy people want to still have the normal notion of matrix multiplication. Right now, you can't even, there's no operator. You have to import the dot function from NumPy and do .a, b to do matrix multiplication. In any case, there's a lot of interesting subtleties to NumPy arrays. And notice they're called arrays, not matrices. Just to emphasize, they should just be viewed as arrays of data, not as something that represents a linear transformation. I'm assuming for the moment that you've all taken 308 or linear algebra class. Okay, so this little bit of code, there's a function toImage that will take such an array and turn it into a PNG image. So for your project involving the Julia set, you may want to use exactly this sort of code to very quickly go from a NumPy array to a PNG file. Okay, and now let's try it out. So, well, there's another thing I want to show you, which is how do you tell Python how to compile this thing? So there's a lot to be said about these really 3 lines of code. So if you look at any of the, say, 45,000 packages that are in PyPy, the Python packaging index, or if you ever download a Python program from somewhere, it's almost certainly going to be a directory with some Python code, possibly some C code, and there'll be a file called setup.py. Okay? And what this does is it's a script. Here's an example of such a thing, which in order to install your program that you've just downloaded, you run that script, and then there's possibly some options you might give. And in my case, because I'm going to use the system-wide copy of Sage, but I want to build everything locally and not have to have permissions to change the system-wide copy of Sage, I'm going to give some options. But if you have your own copy of Sage or Python, you just say Python setup.py install, and it will build any code that needs to be built and then copy it over. So setup.py is the standard in Python for installing a package. Every system, every programming language has something like this. This is just the Python one. So there's some imports. There's a setup function. There's a cython function. If you look at the cython documentation, so I'll show you this page, then it documents this. So basic setup.py has an example of how to use setup.py to describe your Python code to the user. Okay, so it's documented there. But what this does is says that there's a cython module, which is in the file mandel.pyx. There's a whole bunch of defaults, which like what the name of the module will be. It doesn't have to equal the name of this file. You can have multiple. You could have 10 different pyx files all get linked together to make one single module. There's a lot of subtleties. You can have code that your cython, you could have like all kinds of interesting include directories and header files that you have to include from various places. I'm not showing you any of that. This is just the most basic usage. But now that we have this setup.py file, I can do the following. Sage setup py, and then let's see, build extension in place. So actually, let me just do this thing that will fail. Sage setup py install. This is typically what you'll be told to do if you download a Python file and just read the README or something. This will not work if the Sage that got ran is a system-wide copy of Sage. Notice the error, permission denied. If you think that it just worked perfectly, you're not looking closely enough. Notice there's an error in the last line. Pay attention to that. And then the permission denied means I don't have permission to copy the file that it just built into some directory that's, it's like if you were, using your laptop, it would pop up something that says maybe, please enter an administrator password. That's the sort of thing that's happening. So instead, what you do is you give this option, and it will build everything just in this one directory and not try to copy it to some place that you don't have access. Okay, and now here it goes. It built it, and now in this directory, there's a new file called mandel.so. So in Linux and OS X, or any Unix system for the most part, shared object libraries, these are like, it's a collection of code that you can load into a running program that does something that's compiled, are named with .so for shared object. In Windows, they're called, the very similar version of this is DLL for dynamic link library. So just make a note of that. .so is the Unix analog of .dll. In fact, if you were to take exactly this code and run the same thing but in Windows, you would get a .dll instead of a .so. And cython does fully support using Windows. Okay, now what we can do is start up Sage. And now in Python, there's a command import, which you've so far only used to import like libraries that are built into Python or other things that have been installed or Python code you've written. But you can also import certain shared object libraries. This shared object library has some like certain functions that Python expects to be there, which make it so it can be imported. But it's all 100% compiled code. So I've now imported it, and then I can do mandel.tab. And by the way, you could do exactly the same thing inside of a worksheet, except with one caveat: you need to possibly add something to the path, like the current directory to the path. That's done in this worksheet if you want to look at it. But if you do mandel.tab, you can see the functions that are defined there, but also the file names in that directory. It completes on both of them. In particular, there's a function demo, which if we run it, it computes a fractal that's 500 by 500 by default. And then it saves it in a PNG file. If I go back over here to the worksheet, I can then load that fractal. And there you are. You can also run it directly from the worksheet, as I mentioned. So, except there's a big caveat that you should be aware of. Sorry, it showed the output. We can make it bigger if you want, by the way. So let's make it 1,000 by 1,000. See, it takes a little longer, but it's still reasonably fast. And then there's the file. See? There's a caveat, though. If I change the code in that cython module in mandel.pyx and rebuild it, and then re-import it here, it's not going to change anything. It's going to be exactly the same thing that's running. And the reason is that when you import a shared object library with a given name, you can never do that again in the same Python session. Only way you can import that code again is if you recompile it and give this shared object library a different name. So that's just the way shared object libraries work. So what you have to do is restart the process by clicking on restart and then import it again. So watch out for that. If you ever are in a situation using Cython and you are editing code and you're like, wait, it isn't changing even though I keep re-importing it or reloading it, the reason is because you can only do that once. The %cython decorator in the notebook, it gives a random name to the compiled module that it creates. So when you do %cython, that's what it's doing. So that's why it's able to let you import repeatedly. It's actually importing a different one every single time. Okay, so that's almost everything I want to show you. One little thing. It's really like 2 lines long, and it's needed for the homework problem. So this is cython support for external library code. So if you want to call a function that is just a normal C function, the sort of function you might call in a C program, or use a data structure or like a struct, or make a C++ class that is defined in a C++ library, use cdef extern from, and then you declare it right here. So every function that you want to use from the C world directly in Cython, you have to do this. cdef extern from. It's just like some awkward looking thing. And you do colon and you indent, and then you give declarations of stuff that's defined in math.h in this case. So what this will do is it makes it so that for the rest of this Cython program, log, instead of it being what might otherwise be the Python log, actually there's nothing called log, but what it means is that in the rest here, when you type log, like I do down here near the bottom, right there, it's just going to directly call the C log function with no overhead at all. There's nothing. It's just directly, like when it actually turns this into C code, it's going to do nothing. Like that log right there, it's literally just going to be left as log. So the C compiler will get that. And so you get optimal speed. I mean, that's it, but that's the one thing I wanted to show you. There's a lot of variations on this, and you really have to look at the documentation in this page. External C code. So notice there's all kinds of things that you can do, like structs and type defs, and it's pretty complicated. There's kind of a lot of art to it. But it's extraordinarily powerful in that you can just directly call lots of C functionality from your Python. Okay, so now I'm done. And we'll start with the next surprise topic on Wednesday.